Okay, let's unpack this. Imagine you have a robot arm, right? And its job is pretty simple. Pick up a specific thing from a table that's, got stuff all over it. You train it up, and it gets, okay, maybe like a 73.7% success rate first try. Not bad.
Decent, yeah.
But then you totally switch gears. You take the same robot, but now you're training it to predict the future. Like, what's the table going to look like after it does a bunch of actions? And, well, at first it's kind of terrible at it.
Yeah, those predictions can be really fuzzy.
Exactly. Maybe only like a 5.5% exact match on predicting those future states, and you're sitting there thinking, what's the connection here?
Right. Seems like totally different problems.
But then you have this aha moment, picking things up and imagining the future based on actions. They actually share these deep, fundamental ideas, these abstractions.
Like understanding shapes, how things move.
Yeah. Understanding object geometry, predicting physical interactions, filtering out visual junk. It's all connected, deeply connected. Unexpectedly, maybe.
Okay, I see where you're going.
So what do? You train them together. You merge the action-doing part with the world-imagining part.
Oh.
And that, my friends, that's when it really hits you. You didn't just make a robot that's better at picking stuff up. You didn't just make a robot that's better at, imagining the future. You actually trained structured reasoning itself. Welcome to the Deep Dive, where we take your curiosity, add a sprinkle of surprising facts, and get right to the heart of what really matters.
And building right on that really insightful perspective, what we're talking about today is a pretty groundbreaking framework. It's called WorldVLA. So our mission for you today is to really dive deep into this new research, understand how it's pushing the edges of robot intelligence by unifying how robots see, act, and even predict what happens next in their world.
It sounds like a pretty big step.
It really is, towards machines that are much more autonomous, much more adaptable.
Okay, so every great solution, every, big leap in AI, it usually starts because there was a problem, right? What were the limitations? What wasn't working well enough that WorldVLA needed to fix?
That's the perfect starting point.
We've seen amazing progress over the years with something called vision language action models, or VLA models.
Right, RT1, RT2, OpenVLA.
Yeah.
Those kinds of systems.
Exactly. So these are basically powerful AI models. They often take these big, pre-trained, multimodal large language models, MLLMs, the kind of AI that understands text and images, the big models everyone's talking about.
The foundation models.
Right. And they add a special action head or module, basically a piece that tells the robot how to move. They're great at perception. They understand commands. They can decide what action to take.
They see the world, understand your instruction, and generate a move.
Yeah. But here's the snag, and it's kind of a big one. These VLA models, they usually treat actions only as outputs, like, okay, do this.
Right. The action is the end of the process.
Exactly. They don't typically feed those actions back in as input for, deeper analysis. So what that means is, while they know what to do, they often lack a really solid grasp of why doing that action causes a specific outcome in the physical world.
It's like they can follow the steps, but don't really get the underlying cause and effect.
Kind of like following a recipe perfectly, but having no clue about the chemistry of baking,
That's a great analogy. And then on the other side of the coin, you had world models.
Ah, yes, the prediction side.
Right. Pioneered by researchers like David Ha and Jürgen Schmidhuber. These models are actually really good at predicting future visual states. You give them the current scene, tell them what action is happening, and they can sort of imagine or predict what the scene will look like next.
So they understand the dynamics, the visual consequences.
Precisely. They understand visual information, behavioral dynamics, but they aren't typically set up to generate the actions themselves. They're more about understanding what if.
Okay, so that lays out the problem pretty clearly. You've got models that can act, but don't deeply understand why things happen. And models that understand why things happen, but can't really act on their own. How do you get truly smart, adaptable robot control then?
That's the core question, isn't it? And that's exactly the challenge WorldVLA aimed to solve. Its main goal was to tackle these separate limitations by building a single, unified framework, one that integrates both the VLA parts for acting and the world model parts for understanding and predicting, for both action and image understanding and generation, as the researchers put it.
So building a robot that can both do things and understand the results of doing them, all in one brain, basically.
Exactly. One cohesive system.
Okay, so that's the goal, a unified system. But how do they actually build it? It sounds pretty complicated to merge those two different approaches.
It is complex, but the architecture is quite elegant, actually. They designed WorldVLA as an autoregressive action world model.
Autoregressive, meaning it predicts the next thing based on what came before. Like how language models predict the next word.
Exactly like that. It predicts future values, could be the next image frame, could be the next robot action based on its own past predictions and the data it's seen so far. It generates outputs step by step, sequentially.
Okay, that makes sense. And I saw they started with something called Chameleon. Was that like using an existing brain to start with?
Absolutely, a very strategic choice. Initializing from Chameleon gave them a big leg up. Chameleon is already a powerful mixed modal foundation model.
Meaning it handles different types of data.
Right. It's already known for doing a good job understanding and generating images together. So they weren't starting from zero. They leveraged this existing strength in handling different kinds of information, text, images.
Got it. Smart move. So how does this unified model actually process everything? Images, text commands, the robot's own actions. How does it all fit together?
Well, the key is how it breaks down all that information into a common format. Everything, images, text, actions, gets turned into discrete pieces called tokens. And it uses 3 different tokenizers to do this job.
Okay, 3 specialists.
Kind of. First, there's an image tokenizer. Uses something called the VQ-GN model. Basically, it compresses the image data efficiently, turning a picture into a manageable set of codes or tokens for the AI.
Like a summary of the picture.
Yeah, a compact representation. More detail in the image, like higher resolution, means more tokens to represent it. Then there's a text tokenizer. Pretty standard stuff using BPE, bypair encoding. That handles the language commands, pick up the red block.
Standard language processing, okay.
And finally, crucially, there's an action tokenizer. This takes the robot's continuous movements, like moving the arm just so or the exact angle of the gripper, and discretizes them, puts them into bins, essentially. So each specific action gets represented by a small set of tokens, position, angles, gripper state.
Wow, okay. So it's taking vision, language, and physical movement and turning it all into the same kind of digital stuff tokens. That feels important.
It's absolutely critical.
And you mentioned structured reasoning earlier. How does this whole token system tie back into that bigger idea?
That's the magic. This is the crucial link. All 3 of these tokenizers, they share the exact same vocabulary.
The same dictionary for images, text, and actions.
Exactly. And this isn't just a technical detail, it's the foundation for that structured reasoning. Because they share a vocabulary, tokens from these different sources, seeing, being told, doing, can all be processed and understood together within the single LLM architecture.
So the model learns the relationships between seeing a block, hearing pick up the block, and the actual tokens for the arm movement needed.
Precisely. It's like it learns a universal language that connects perception, instruction, and action. This allows it to build these complex internal models, linking visual cues to commands, predicting the physical results, all in one integrated thought process. That's what we mean by structured reasoning, seeing the connections, the whole picture, not just separate data streams.
That is a powerful concept. Okay, so they built this elegant, unified system. But you mentioned challenges. What happened when they tried to get the robot to plan like multiple steps ahead, generating these action chunks?
Right, planning sequences of actions. That's where they hit a pretty significant snag initially.
What went wrong?
Well, if you just use a simple autoregressive approach, generate action 1, then use action 1 to generate action 2, and so on, the performance just tanks.
It falls apart.
Yeah, significantly. Yeah. We're talking potential drops of 10% to even 50% in grasping success.
Wow. Why? What causes that?
It's error propagation. Basically, if the model makes a small mistake generating the first action in the sequence, that mistake influences the generation of the second action, which might then be even more off.
Like a game of telephone.
Exactly like telephone. The errors compound. Remember, these big MLLMs are amazing with text and images, but their innate understanding of robot actions, especially sequences, isn't as strong initially. So they tend to over-rely on the action they just generated, even if it was slightly wrong, instead of looking closely at the fresh visual information from the camera.
So the error just builds and builds.
Right, leading to a cascade of mistakes.
Okay, so how did they fix that? That sounds like a fundamental problem.
It was, and their solution is really clever. They introduced a novel technique called an action-attention masking strategy.
Action attention masking. Okay, what does that do?
It's a modification to the attention mechanism. That's the part of the AI that decides what information is most important to focus on. This special mask selectively hides or masks the immediately preceding actions within the same chunk when the model is generating the current action.
So when it's deciding action number 3, it doesn't pay too much attention to the action number 2 it just decided on.
Exactly. Within that sequence or chunk, it's planning. Instead, it forces the model to generate the current action based primarily on the original text instruction and, crucially, the latest visual input from the robot's sensors.
Ah, so it relies more on what it sees now rather than what it just did.
Precisely. It stops that telephone game.
Yeah.
It drastically reduces that error accumulation problem.
When did it work? What were the results?
Huge improvements. This masking strategy led to substantial gains in generating these action chunks accurately. We're talking a 4% to 23% improvement in grasping success rate compared to the naive approach. It prevented that performance degradation.
That's a big difference. A really smart fix to stop the errors compounding.
Definitely a very elegant solution to a tricky problem.
Okay, so we have the unified system. We have the clever masking strategy. What did this all add up to? How did WorldVLA actually perform on, real robot tasks? Did unifying everything really make that much of a difference?
It absolutely did. The researchers found really compelling evidence for what they call mutual enhancement.
Mutual enhancement, meaning the parts help each other.
Exactly. The action model part and the world model part actually make each other better because they're integrated and learning together. They tested this rigorously using a standard benchmark called Libero.
Libero. What does that involve?
It's a collection of diverse robotic tasks designed to test different capabilities. Spatial reasoning, handling objects, reaching goals, even tasks that require long sequences of actions. It's quite comprehensive.
Okay, so what were the key results? What really jumped out from the Libero tests?
Well, first, they clearly show that the world model helps the action model.
A lot.
By integrating that predictive world model, the robot gets much better at acting intelligently. Because the world model learns the sort of intuitive physics of the environment by predicting what happens next visually. It allows for what they term prospective simulation.
Meaning it can kind of play out scenarios in its head before moving.
That's a great way to put it. It evaluates the potential outcomes of different actions before committing. This leads to much more informed decisions.
Any cool examples of that?
Yeah, they showed examples where WorldVLA would say, try to grasp an object, maybe fail, and then keep trying different grasp approaches until it succeeded before moving on to the next part of the task, like putting the object somewhere.
Unlike a simpler model that might just fail the grasp and move on regardless.
Exactly. Standalone action models might just go through the motions. WorldVLA showed more persistence and understanding of whether the subtask, like grasping, was actually successful. It knew if it had the cheese of the bottle before moving it.
That feels much more intelligent, more aware. Okay, so the world model helps the action model. What about the other way around?
Yep, equally important. The action model helps the world model too.
How does the doing help the predicting?
Integrating the action information actually helps the world model generate better, more accurate predictions of the future, especially for longer sequences. The actions provide context that makes the visual prediction less ambiguous. It leads to more accurate visual interpretation and a deeper understanding of behavioral patterns.
So performing actions helps it learn how the world really works visually.
Right. Qualitatively, they showed WorldVLA generating video predictions that were much more coherent and physically plausible. In scenarios like opening a drawer or moving objects where a pure world model might predict weird things, like objects vanishing or moving strangely, WorldVLA's predictions looked much more realistic because it understood the actions involved.
That's fascinating. A real two-way street. Both parts genuinely make the whole system smarter. What else did they find? Did things like camera quality matter?
They did look at the impact of image resolution. And yes, higher resolution helped. WorldVLA performed better using 512 2x512 pixel images compared to 256 by 256.
Why was that? Just more detail.
Partly, yes. Especially for tricky grasping tasks, more detail helps. But also, the chameleon model they started with was originally optimized for that 512 2x512 resolution, so it was naturally better tuned for it.
Makes sense. Did they compare their world model approach to just using a generic video prediction model?
They did, and the finding was clear. The world model, which is explicitly conditioned on the robot's actions, was consistently more helpful for the action model than a general video prediction model that doesn't know what action is being taken.
Why the difference?
Because knowing the specific action removes ambiguity. If you just predict video, lots of things could happen. If you predict video given this specific action, the prediction becomes much more constrained and relevant, leading to less noise or inconsistency during training, as the researchers put it. The robot benefits more from predicting the direct consequences of its own intended actions.
Right, it's predicting something directly useful for its own decisions.
Exactly. They also found that using multiple past image frames, they use two by default, help performance, especially for those tricky action chunks. It gives more visual context about motion and dynamics.
Like having a bit more short-term memory of what just happened
Yeah,
visually.
precisely. And one last key finding. Pre-training the action model using the world model gave notable improvements. Basically, letting the world model teach the action model about visual dynamics before fine-tuning the action model directly made the robot better at grasping.
So letting the predictor part school the doer part first was beneficial.
Exactly. It helps bootstrap the understanding of physics and consequences.
Wow. So pulling it all together, what we've really seen with WorldVLA isn't just, a slightly better robot arm. It feels like a fundamental shift.
I think that's fair to say.
It's not just about teaching it to see or teaching it to move, but teaching it to connect those things, to reason about its actions and what happens next in the world. Like you said earlier, it's building a bridge between perception, language, and physical reality, not just parsing commands.
That's a great way to summarize it. And if we zoom out to the bigger picture, WorldVLA really points towards a future where robots aren't just blindly executing instructions. They'll have a deeper understanding of their environment, the physics involved, and they'll be able to anticipate outcomes. That leads to much more robust, flexible, and general-purpose AI.
And are the researchers stopping here? What's next?
Oh no, they have plenty of ideas for future work. They talk about scaling things up, bigger models, more data, designing potentially an even better, truly unified tokenizer that handles vision even more effectively, and maybe even adding a sort of secondary specialized action head just to further boost grasping precision. Lots of avenues to explore.
Sounds like they're just getting started.
It feels that way, and it leaves us with a really interesting thought, doesn't it? As we continue this deep dive into intelligence, if AI, like WorldVLA, can learn this structured reasoning across seeing, acting, and predicting physical interactions, what other fundamental abstractions might AI uncover next? What other bridges might it build?
And what does that mean for our understanding of intelligence itself?
Exactly.
Yeah.
A question to ponder.